In this video, we'll be talking about a machine learning algorithm called Perceptron. Perceptron is probably the machine learning algorithm with the scariest name, but also relatively easy to understand. So let's get to it. The first thing we'll talk about is when you should use Perceptron. Of course, certain machine learning algorithms are more applicable in certain situations than others. So when should you use this one, Perceptron? The answer is when a dataset is linearly separable. Sounds a little bit scary, but let's look at a picture which kind of clearly shows what it is. On the left, I have a dataset that is linearly separable. On the right, I have one that is not. You can probably already see the difference, but just to kind of say it, it's that you can draw a line which separates the two classes you're trying to identify. Here the two classes are the x's and the triangles, and we see here this red line clearly separates the x's from the triangles. Of course, there's other lines we could have drawn with different slopes that would also work, but the point is there exists at least one line that does the job for us. Now, in contrast, on the right, we see that even though there's a natural clustering, and what we really want to draw here is a circle, right? If we could, we would want to draw this circle, which separates the two data sets. But the point is, for Perceptron's sake, there's no line I can draw such that all the x's will be on one side and the triangles will be on the other. So we can't use Perceptron as it is in this case. But keep this case in mind, because we're going to be able to do a quick extension to Perceptron at the end of this video, which will take care of that case. So don't worry. The next thing we'll talk about are what are the parameters and inputs for the Perceptron. And the good news here is that there's only two parameters, and the input is, of course, the x1 and x2. You can also think of it as x and y, but we'll be calling it x1 and x2 coordinate of each point here that we're trying to identify. So let's go to the parameters first. The parameters for Perceptron, the first one is this omega, which is a vector, which is the number of dimensions you have plus one. So here we're working in 2 dimensions, so we have 3 elements in the omega matrix. The reason we have one more than the dimension is because we need a constant term, but that'll become more clear in a second. So omega here is consisting of omega naught, omega 1, and omega 2. Now these are known as our coefficients, and they're going to kind of tell us what the line looks like, which we're using to potentially separate our two classes, so that we can judge whether that line is or is not effective in doing that job. More on that later. The other parameter is called nu, this Greek letter if you're not familiar, nu, which is going to be known as our learning rate. We'll be seeing this in action in a little bit, but you can think of the learning rate as how fast the Perceptron algorithm converges to this line which separates the two classes. So basically the trade-off here is the higher you make the learning rate, the faster it's going to take steps, but that also means that it might be overshooting more often. The lower you make the learning rate, the slower it's going to make progress towards that optimal line, but it also means that you're probably going to make less mistakes along the way. So that's the kind of trade-off between setting a higher low nu learning rate. And of course the input is this vector, which again also is has 3 elements, one more than the number of dimensions we have, because we need this first element to be always 1 as the constant term. The other elements are the x and y, or x1 and x2 coordinates of each data point we're trying to classify. Now that we have our parameters and we have our inputs, how do we put them together to figure out which class any given data point should be in? It's really, really simple. We just take a dot product. So for those of you who are not familiar, a dot product between 2 vectors of the same size, in this case omega and x, is simply what you want to do is take the product of each element and add them together one by one. So to kind of explain it in a better way, you take omega 1, you take omega naught times 1, you take omega 1 times x1, omega 2 times x2, and you add up those products together. So we see that's exactly what we've done here. Notice here this omega naught is by itself because the x naught is just 1, so it doesn't really factor in. So we take that quantity right there, again, which is a dot product between the omega vector and the x. You can think of it, if you know more linear algebra, you can think of that as omega transpose x, another way to look at the dot product. If that doesn't make sense to you, don't worry about it. You take that quantity. If it's bigger than 0, then you assign that data point as an x. If it's less than or equal to 0, you assign it as a triangle. And that's really it. That's how Perceptron classifies any given data point. Now, this was probably all kind of confusing because all we did was look at some math. How does that math translate to some of these pictures we're looking at earlier? Let's take a look at that now. So what we'll do first is assign some concrete values to omega so that we're not working in complete theory for the rest of this. So right here, we see that omega is going to be the vector 0, 1, and 0.5. And of course, x is the same 1, x1, x2. So what does that mean? So for any given input, x1 and x2, of course the coefficient term, what we do is do that 0, so the first element of the omega vector with this 1 here, this 1 in the omega vector with the x1 and the 0.5 with the x2, we do the corresponding multiplications and we add them together, which is the quantity you see right here. And what we do is check if that's bigger than 0, right? Because from the previous sheet, if that's bigger than 0, we assign it as an x. We check if it's bigger than 0. Now, if you take this inequality right here, this dot product bigger than 0, and you simplify it, what you're going to get is x2 is bigger than minus 2x1, which is just the equation of a line in the plane, right? And which line is that? So we see that that line is just given by this right here. So this black line I've drawn right here is x2 equals negative 2x1. So anything above that black line will be categorized as an x, and anything below that black line will be categorized as a triangle. Let me just draw a little bit more of that line so it's clear. So we see that that's how Perceptron works. That's how we take the omega vector that Perceptron requires and translate that into a line in the plane. And let me just take a moment here to qualify that everything we've been saying applies for higher dimensions. I'm just drawing in 2D because that's how it works on paper, but this of course works for 3 dimensions, 4 dimensions, and higher. It's just that these lines become planes and hyperplanes and so on. Okay, so keep that in mind as well. Now, looking at this picture, do we see that everything is okay? Well, remember we said that if it's greater than 0, it gets assigned as an x. If it's less than or equal to 0, it gets assigned as a triangle. Are these points all correctly classified? Let me pull out a red marker to figure out if any are wrong. So remember, below the line, triangle. So this guy, fine. This guy, good. This guy, good. Above the line, x. This guy, good. This guy, good. This guy, good. But we have an issue now. This one triangle here is above the line that we have currently, yet it should be with the triangles which are below the line. So we need to be fixing this line so that it more accurately captures the division in our data set. And we see that it is possible. We see that, I'm going to use this stick here, we see that if we had this as our line, we would totally classify everything correctly because we still have these 4 triangles below and we have these 3 x's still above. So it is doable. We just need to update our current line so that it gets us where we want to go. That brings us to the update step of Perceptron, which is given that we have a current omega vector, how do we generate a next omega vector which is more suitable for our goals? That update step in math terms, of course, we'll go down and do all the real numbers here so it's not just theoretical, but in math terms first, for each element in the omega matrix, omega 1 prime, this is going to be the new one, right? So let me just explicitly say this is the new element of the omega matrix vector, and this is the old one without the prime. So the new one is given by the old one plus the learning rate. This is where that learning rate factors in, new, times d. D is defined just below, so we'll do that in a second, times the corresponding x value. So if we're trying to update omega 2, then this is going to be x2 of the misclassified point. In this case, the misclassified point is at 2, minus 2. So the x2 would be negative 2, okay? Now the question is, what is this d? This d is really simple. This d is just 1 if the misclassified point should be in the upper set, and it's negative 1 if it should be in the lower set. So our point here, this triangle, should be in the lower set with its other triangles. So d will be minus 1 for us, okay? And that's it. Now we're going to go through, well, I won't actually go through all these calculations, but you see that I've taken this formula here, and I've applied it to omega naught, omega 1, and omega 2. I want to generate the new ones of all those, right? So I go through the math. Remember, let me just go through one of them for simplicity. So omega naught, what was omega naught? It was 0, so that's why I have this 0 here. Plus new, the learning rate, I've set as 0.2, okay? You can set it higher or lower if you want. Remember the trade-off. D, which is minus 1, right? Because we want it to be in the lower case. And then x naught. X naught is, of course, always 1. When I do all that, I get my new omega naught prime, is negative 0.2. I do the same parallel calculations. I get my new omega 1 prime is 0.6. My new omega 2 prime is 0.9. Now, let's go ahead and switch to this sheet really fast. And we see that if I do my dot product now with this new omega vector, so this quantity right here is the new dot product. You can recognize this as the new omega naught prime. Remember, this guy is the new omega 1 prime. This guy's new omega 2 prime. And the stuff they're getting multiplied by is the same 1, x2. When you reduce all this, what you get is x2 is greater than negative 2/3 x1 plus 2/9. And what does that look like on our graph? So I'm going to use this stick I have a little helper line drawn so I don't have to do it on the fly, but lining that up, that is what that new line looks like. And we see that correctly classifies the points. Of course, this triangle looks like it's on the border, but it is clearly below. So we see that this new line classifies all points correctly. It's important to note that a new line might take a previously correctly classified point and make it incorrect, but that didn't happen in this case. So all these x's that were correct before are still correct. They're still above that new line. And the more important part is that these triangles are still correct, and this new triangle, or this triangle that we were trying to fix, got fixed. So we're all good. We can stop here. Everything is classified correctly. But if it were not, we would just take the next misclassified point and run it through these update steps again and keep going again and again and again until either we get everything correctly classified or we reach some other stopping criteria, like we've done 100 iterations or we're some distance away from our goal or something. So that is how Perceptron updates. The last thing I want to talk about is an extension of Perceptron when the dataset does not look necessarily linearly separable, but it does look like we can separate it in a different way. So this is going back to that beginning case where we have this data set, and of course there's no line I can draw through it which is going to separate the x's from the triangles, but there is a circle I can draw through it. So how do I use that to my advantage? We use polar coordinates. So remember, polar coordinates map a Cartesian coordinate system, this xy, to r theta, which measures, r of course measures how far away a point is from the origin, theta measures which angle it is from the origin. Starting with angle 0 here, we go counterclockwise, of course, in trigonometry. We reach pi here, or we go around back the other way and we reach minus pi here. Okay, so in this case, we see that this inner circle more or less maps to this kind of distribution because there are all different kinds of radiuses. They're at all different kinds of thetas, but they're around the same radius, clustered around this R1, let's say. And this outer circle are at all different thetas also, but they're more or less around the same bigger radius, some R2. So when we map this previously not linearly classable data set, linearly separable data set into polar coordinates, we get this new data set. And this, as we see, is easily linearly separable. For example, this line will do the trick. Many others will do the trick, but this one will do just fine. So don't lose hope if a data set doesn't look linearly separable. Try to convert it into polar coordinates or some other coordinate system that's going to get you into that linearly separable case. This was a quick introduction to the perceptron algorithm in machine learning. So until next time.